up is Sam talking about lightning computational graph theory.
All right. Cool. You guys see this? All right.
I love
This
this
is
slide.
cool. This is a copy of a presentation I've done before. Here are the slides. Here are the original slides. All right. Real quick, what is a graph? A graph is a common data structure that shows up a lot in computer science. It is the collection of points and the arrows that connect to them. Points sometimes called vertices or nodes, arrows called edges. Mathematically speaking, a graph is a structure containing two sets, a set of vertices and a set of edges. Vertices such that each one is unique and can be uniquely identified, and that each edge directly connects two vertices in the list. Vertices and edges can also contain additional information, which makes just about everything a graph, from the parliamentary structure of Iran to the British line of succession, DAG, to a company's organization chart, a tree, to the Domino's pizza tracker, a list. So this is the kind of hierarchy here. In the set of things that are graphs, a subset of them are DAGs, directed acyclic graphs, graphs with no cycles in them. A subset of those are trees, which are graphs that have one root starting node. And then a subset of those are lists, which are trees that are just really lopsided. All right, so when we talk about things we want to do with graphs, there are four key operations that we like to do with them. We like to traverse the graphs, and in particular, we want a unique guaranteed traversal between 2 points in the graph. We want to store and serialize the graph, and in particular, we want isomorphic serialization so that we can write the graph out identically the same time, and that gives us fast equality operations. And we want to be able to modify and look up edges and nodes in the graph quickly. So lines and linked lists are excellent graphs. You're able to traverse them in linear time, and you're able to store them in linear space. And there are heuristics for being able to append in constant time and look up nodes in a graph in constant time. Trees are a bit more complex, but still, we are able to traverse a tree in linear time. And there is a mechanism to store and serialize a tree in a linear fashion with some additional overhead. And a well-balanced tree can, on average, get logarithmic time performance for insertions and deletions, which is very effective. And then we have directed acyclic graphs. The focus is now no longer on the vertices, but on the edges. And still using an edge list implementation, we are still able to get linear time and traversal and storage, and able to still operate on the graph effectively. So looking at this picture, we're still able to, at worst case, get linear time on all of these operations on all of these kinds of graphs. Still better time with lists and better average time with trees. However, by the time we're starting to get into directed acyclic graphs, there are multiple ways to traverse a DAG, and as a result, we lose our guarantee of unique traversals. Not to mention there are different ways to serialize DAGs out, and so there's we lose our isomorphic serialization, which makes equality operations difficult. But the moment we add even a single cycle into the graph, complexity goes through the roof. If we're traversing our graph of a naive depth-first search implementation, trying to go from A to G, we'll go ABD, 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 and hit a loop. And that becomes problematic. Cycles and graphs are not customer friendly. You ever play Chutes and Ladders? Chutes and Ladders is a terrible game. What's the big O complexity of Chutes and Ladders? It's infinite. There's a theoretical rolling of the dice where that game never ends. Joseph Heller wrote a book about traversing cyclic graphs. It's called Catch-22. And so when you start having cycles in your graph, you have to reach for more exotic data structures in order to deal with these, such as hash table implementations, whose complexity starts to involve both the number of vertices and the number of edges. And so things start to get really complex. One kind of complex graph is a bidirectional graph, where all of a sudden the edges go in each direction.
1 minute, Sam.
Got it.
1 minute.
So if you have a graph like this, you think maybe, all right, at least from any node, we can get to any other node, right? Wrong. Just because a graph is bidirectional doesn't mean it's fully connected. And so there's not a direct path from Y to B or any of these other nodes. Directional graphs make all kinds of weird references. They make self-references, which aren't even funny. They're just meta. And so you have, when you have graphs of this structure, you have to start reaching for adjacency matrices, which do not scale with regards to the number of vertices, but at least you could still modify the edges in a reasonable time. And so this is the big picture. Graphs performance is a crapshoot. They're hard to maintain. Customers hate being stuck in a graph problem. Computers hate dealing with fees. In general, try to avoid the graph problems because good computer science happens at DAG or better. And that's my presentation.
And time. Nice job. That is exactly
Nice,
fine.
dude.